In the realm of quantum physics, there exists a phenomenon so bizarre and counterintuitive that even Albert Einstein himself could not fully embrace it. He famously referred to it as spooky action at a distance, a term that captures the enigmatic nature of this quantum peculiarity. This phenomenon is known as quantum entanglement, and its implications have the potential to revolutionize our understanding of the universe and our place within it. Today, we embark on a captivating journey to explore the world of quantum entanglement, its history, its applications, and its profound impact on the future of science and technology. At its core, quantum entanglement describes a situation in which two or more particles become inextricably linked, such that the quantum state of each particle cannot be described independently of the others, even when the particles are separated by vast distances. This means that measuring the state of one entangled particle instantaneously affects the state of its partner, regardless of the distance between them. This strange and seemingly impossible connection defies our classical understanding of the world and challenges our notions of locality and causality. The story of quantum entanglement begins with the birth of quantum mechanics itself. In the early 20th century, physicists such as Max Planck, Niels Bohr, and Werner Heisenberg began to unravel the mysteries of the subatomic world, discovering that the behavior of particles at the quantum scale was governed by a set of rules that seemed to defy common sense. One of the most startling revelations was the realization that particles could exist in multiple states simultaneously, a phenomenon known as superposition. It was against this backdrop that Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a seminal paper in 1935 that introduced the concept of quantum entanglement. The paper, known as the PR paradox, sought to demonstrate that the strange predictions of quantum mechanics were incomplete, and that there must be some hidden variables that could explain the apparent paradoxes. The thought experiment proposed in the paper involved two entangled particles, separated by a large distance, and showed that measuring the state of one particle would instantaneously determine the state of the other, a result that Einstein believed was impossible according to the laws of special relativity. The PR paradox sparked a heated debate among physicists, with many of Einstein's contemporaries, including Niels Bohr, defending the completeness of quantum mechanics. It wasn't until decades later, in the 1960s, that physicist John Stuart Bell proposed a way to test the predictions of quantum entanglement experimentally. Bell's theorem, as it came to be known, showed that any theory that sought to explain the behavior of entangled particles using hidden variables would have to violate the principles of locality and causality. The first experimental tests of Bell's theorem were conducted in the 1970s and 1980s, using entangled photons generated by atomic cascades. These experiments, performed by researchers such as John Clauser, Elaine Aspect, and Anton Zeilinger, provided strong evidence for the reality of quantum entanglement and the validity of quantum mechanics. Since then, numerous experiments have confirmed the predictions of quantum entanglement with ever-increasing precision, ruling out many alternative theories and cementing the status of entanglement as a fundamental feature of the quantum world. As our understanding of quantum entanglement has grown, so too has our appreciation for its potential applications. One of the most exciting of these is in the field of quantum computing, where entanglement is harnessed to perform complex calculations that would be impossible for classical computers. In a quantum computer, information is stored in quantum bits, or qubits, which can exist in multiple states simultaneously thanks to superposition. By entangling these qubits, quantum computers can perform certain tasks, such as factoring large numbers or simulating complex chemical reactions, exponentially faster than their classical counterparts. Another promising application of quantum entanglement is in the field of quantum cryptography, which exploits the properties of entangled particles to enable secure communication that is theoretically unbreakable. In a typical quantum cryptography protocol, a sender and receiver share a pair of entangled particles and use the states of these particles to encode and decode messages. Any attempt by an eavesdropper to intercept the communication would disturb the entanglement, alerting the parties to the breach and rendering the information secure. Beyond these practical applications, quantum entanglement has also shed light on some of the deepest questions in physics and philosophy. One of the most profound implications of entanglement is that it seems to challenge our traditional notions of causality and the nature of reality itself. If two entangled particles can influence each other instantaneously across vast distances, does this mean that there is some hidden connection between them that transcends space and time? Some physicists have even suggested that entanglement could be a clue to the nature of spacetime itself, with the fabric of the universe being woven from a vast network of entangled particles. Another deep question raised by quantum entanglement concerns the role of observation in shaping reality. In the quantum world, the act of measurement itself can have a profound effect on the state of a system, causing it to collapse from a superposition of multiple states into a single definite state. This has led some philosophers and physicists to propose that consciousness itself may play a role in determining the nature of reality, an idea that has been explored in various interpretations of quantum mechanics, such as the Copenhagen interpretation and the many worlds interpretation. Despite the profound implications of quantum entanglement, much about this strange phenomenon remains unknown. One of the biggest challenges facing researchers today is understanding how entanglement scales up from the microscopic world of particles to the macroscopic world of everyday objects. Some physicists have proposed that there may be a limit to the size of objects that can be entangled, while others have suggested that entanglement could be a universal feature of the universe, with everything from stars and galaxies to living organisms being connected by a vast web of quantum correlations. Another open question in the study of quantum entanglement concerns the nature of the speed of the interaction between entangled particles. While experiments have shown that the effect of measurement on one particle is instantaneous on its entangled partner, regardless of the distance between them, it is still unclear whether this interaction truly defies the speed of light or whether there may be some hidden mechanism that allows for faster-than-light communication without violating the laws of relativity. As research into quantum entanglement continues to advance, it is becoming increasingly clear that this bizarre phenomenon is not just a quirk of the subatomic world, but a fundamental feature of the universe that has the potential to transform our understanding of reality itself. From the development of powerful new technologies like quantum computers and unbreakable encryption to the exploration of the deepest questions of physics and philosophy, the study of entanglement promises to unlock new frontiers of knowledge and discovery. Perhaps most exciting of all is the possibility that our growing understanding of quantum entanglement could one day lead to a grand unified theory of physics, one that reconciles the strange and counterintuitive world of the quantum with the elegant and predictable world of classical mechanics. Such a theory would not only provide a more complete understanding of the universe at its most fundamental level, but could also open up entirely new realms of scientific and technological possibility, from the creation of exotic new materials with unprecedented properties to the development of technologies that harness the power of quantum mechanics in ways we can scarcely imagine. As we continue to unravel the mysteries of quantum entanglement, it is clear that we are only just beginning to scratch the surface of this fascinating and endlessly complex phenomenon. With each new experiment and theoretical breakthrough, we are reminded of the incredible beauty and strangeness of the quantum world, and of the limitless potential that lies waiting to be discovered. Whether we are probing the depths of the subatomic realm or exploring the furthest reaches of the cosmos, the study of entanglement promises to be one of the great scientific adventures of our time, a journey that will challenge our assumptions, expand our horizons, and ultimately deepen our understanding of the universe and our place within it. So the next time you hear about the latest advances in quantum computing, cryptography, or fundamental physics, remember the strange and wonderful world of quantum entanglement that makes it all possible. And as we continue to explore this endlessly fascinating realm of science, let us never lose sight of the sense of awe and wonder that drove Einstein and his contemporaries to probe the mysteries of the quantum world, and that continues to inspire new generations of scientists and thinkers to this day. For in the end, it is this spirit of curiosity and discovery that will lead us to new frontiers of knowledge and understanding, and that will help us to unravel the secrets of the universe, one entangled particle at a time.